Yeah, next week you're going to have your practical session also, right? Yeah, to prepare yourself for your practical session, make sure you have the MATLAB installed. All right, so you can use the evaluation version of MATLAB. Okay, then that will be for your practical session. I will upload your lab manual this week so that you can have a look, and maybe to prepare yourself better, you may want to go through the lab manual first before your practical session. I think that will actually give you an idea. Um, if you actually done your revision for the test, then I think the practical session manual should be okay. You should be able to understand it. If not, then you might be struggling, during the practical session. The practical session is only 2 hours, so it's from past experience is quite short to some people who are not prepared. So I'll advise you to actually get yourself ready by going through the manual, and may want to try out some of um, the procedure in there. All right, and how to construct the blocks, and where to get the blocks. So because you're now in year 3, so I won't actually go through the lab manual line by line or page by page with you. All right. So I expect you to actually read the manual and do it on your own. Yeah. Then during the practical session, I will ask you to actually upload your simulation results. Okay, even though report is not required for this practical session, you will have to upload your simulation results to Google Classroom, just to make sure that you actually get the correct result lah. Yeah, and if you cannot get the correct result, then you can always raise question, and then I will try to help you out there. Okay, so don't wait until last minute only you install, because from past experiences, some students take, I don't know, more than 1 day to install. So if you try to install maybe 2 hours before the session, you will not be able to get it done. All right. Okay, this on your practical session. Okay, another thing. For tutorial 2, I have actually completed tutorial 2. But I noticed that there is one exercise that I asked you all to do and upload, which is question 4 on tutorial 2. Quite a number of you haven't actually uploaded your spectrum into Google Classroom. And upon checking, I found that most of them actually come from group 2. Group 2. So I'm not sure whether you're not aware of it or I did not inform you. All right, so please get tutorial 2 question 4 done, and then upload your answers into this assignment in your classroom. Yeah, no mark will be given, just for me to check that you are able to do it. All right. Okay. All right, what else? Okay, so these are the few important announcements. So as far as today is concerned, I want to finish off the lecture on frequency modulation. And then I'll move on to discuss some of the tutorial questions for this chapter. All right, so I won't start new chapter this week. So I will again make use of the Wednesday lecture session to also discuss tutorial questions. So make sure you attend the lecture session as well. All right. So let me get started on your lecture. Anything you want to say about your um, midterm test? Any questions on your midterm test? No? Okay, then I will start the lecture then. So for today's session, I'm going to finish off this chapter on frequency modulation techniques by going through the demodulation process. Okay, as far as the FM demodulation is concerned, there are two methods. They are commonly used. All right. So the first one is the direct method. So in the direct method, we actually make use of a FM detector or discriminator. And in the indirect method, we make use of a phase lock loop. So the block diagram here actually show you the processing blocks inside a direct FM demodulator. All right, so the FM signal, all right, traveling through the channel will have noise added to it. All right, so when it arrives at the receiver, the first processing block is a bandpass filter. All right, so the function of this bandpass filter is to remove any signal outside the bandwidth of the FM signal that we're interested with. All right, so therefore the noise is again limited to this limited by the bandpass filter to a bandwidth of the transmission bandwidth of the FM signal. And FM signal, we expect FM signal to actually has a constant amplitude, and therefore the filtered FM signal is then passed through a limiter to remove any amplitude variation. So that means the output of this limiter, the amplitude of the signal will be constant. All right, the signal is then passed through a discriminator. A discriminator basically is a device with the output that is proportional to the deviation in the instantaneous frequency. Okay, this is what we want, isn't it? Because the as far as FM is concerned, our message is actually represented by the frequency of the signals in the FM modulation techniques. Yeah. So the discriminator basically it will recover the message signal. All right. So the output, the amplitude of the output signal is proportional to the change in the instantaneous frequency. All right. So remember when we perform modulation, we actually translate the amplitude of the message to frequency, right? And therefore, in the demodulation process, we do the reverse conversion, where we actually convert the change in the frequency back to amplitude. And then the output signal is then passed through again a low pass filter, all right, to recover the baseband signal. All right, and this filter, again, the bandwidth is the bandwidth of the message signal W. So any noise outside this bandwidth W will be removed as well. Yeah. So what is discriminator then? Frequency discriminator, okay, there's a note down there. Basically, it's a demodulator that consists of a differentiator. All right, remember in the modulation process, we actually integrate our message signal. All right, so therefore, in the demodulator, we need to have a differentiator that undo the integration. So therefore, we need a differentiator. And then inside this discriminator as well, there will be a envelope detector. The envelope detector is very similar to the one we actually use in the demodulation of a FM of a AM signal. Okay, so this is how a discriminator look like. All right, so the FM signal, all right, where it has the frequency change according to the amplitude of the message signal. All right, constant amplitude. This is the characteristic of a FM signal. So the differentiator will actually convert the change in the frequency, all right, to change in amplitude. So therefore, if you look at the amplitude variation of the output of a differentiator, is very, very similar to the double sideband full carrier signal, isn't it? This is basically this is the envelope that represent the message. All right, and then the carrier, again, for double sideband full carrier signal, the carrier frequency is constant. But in this case, the carrier frequency is not really constant, but the envelope is similar to the double sideband full carrier signal. So we just want the we just want the amplitude information, because now the message are all contained in the amplitude already. All right. So therefore, we can actually make use of an envelope detector that actually detect this envelope. All right. The envelope basically is our message signal. And of course, we actually pass it through a DC blocker to actually remove the DC component and recover our baseband message signal here. And then for indirect FM demodulation, making use of phase lock loop, basically we have a phase detector. All right, so the phase detector basically produces a low frequency output voltage that is a linear function of the phase difference between the two input signal. And what are the two input signal? The first input signal is the FM signal that comes in. All right, the second input signal basically is the output of a voltage control oscillator. All right, so what is this voltage control oscillator? This voltage control oscillator basically, all right, is the block that actually take in the input voltage, all right, and then the output basically changes. The output frequency varies with the input voltage, right? Um, okay, so the difference between the phase angle of these two input of the phase detector will actually then be passed through a low pass filter. All right. So again, the function of a low pass filter here is to pass the low frequency component, which is our message, and then at the same time, it also remove the out of band noise. Yeah. Then this filter signal is then amplified. All right. Then the output of this amplifier is then fed through the voltage control oscillator. All right. So this become a control voltage. Right. Then the output of a VCO then is fed back to the phase detector again. All right. So when the loop is in lock, then the VCO or the voltage control oscillator frequency will actually follow the incoming signal frequency. So basically, we actually want to log in, find out what is this input signal frequency is. Okay, so here there is some mathematical derivation as well as proof. All right, that the output signal basically is a form of your message signal. All right. So here the instantaneous frequency of a FM wave is basically given by the carrier frequency. All right, plus the variation in the carrier frequency that is caused by your message, right? Your KFMT, right? Where MT is your message, KF is your um, frequency sensitivity, right? Of your FM modulator. Then the instantaneous frequency of the VCO, all right, is given by F naught plus KVCO V naught T. So what is F naught? F naught basically is the free running frequency of the VCO, all right, and KVCO is the frequency deviation sensitivity of the VCO, all right. Um, So for the VCO frequency to track the incoming frequency, that means the FVCO need to be the same as your F in frequency of your input signal. All right. So if we replace the expression for FVCO and FI, then we're going to get this equation. All right. So when the phase is locked, that means the F naught actually is same as FC. All right. So when F naught is same as a FC, therefore your VO, the output voltage, all right, basically is a, a linear version of your MT. All right, where KF and KVCO are both constant. All right. So basically your output signal is proportional to the original message signal. Okay. Okay, so here we're actually at the end of the chapter now. So it actually makes sense to make some comparison between the AM and the FM techniques that we have studied so far. So this slide actually show you the advantages of FM as compared to AM. All right. So as far as FM is concerned, all right, we know that it has better immunity to noise. All right. Why? Because our message is actually contained in the frequency. All right. Well, most noise is amplitude based. Yeah. Whereas for FM signal, the amplitude is always constant. Yeah. So any variation to its amplitude, we're not worried because later on we're going to uh, limit the amplitude with the limiter. Yeah. So as far as the message is concerned, the message is contained in the frequency variation. So we're not so worried about the noise, which is amplitude based. Yeah. Whereas for AM techniques, our message is contained in the amplitude. Therefore, the amplitude modulated signal is very, very sensitive to noise. Okay. So any noise will actually affect your AM signal. And the second advantage of frequency modulation technique is that it's actually resilient to signal strength variation. Again, this comes from the fact that the frequency modulated signal has constant amplitude. Right. So any variation in the signal strength, uh, we can always change chip back to constant. Right. And this is ideal for use in a mobile application where our signal level actually vary according to the condition of the channel. Right. So when the signal level drops, we can always boost it back. Yeah. Because for as far as FM is concerned, our amplitude is constant. So our signal level should be constant all the time as well. Whereas for amplitude modulation, again, our amplitude of our AM signal varies according to the modulating signal, isn't it? So therefore, it's actually very sensitive to signal strength variation. Yeah. And then the channel condition, the channel may also change the amplitude as well because of the channel, some of the channel that it goes through, the message or the amplitude might be affected. All right, again, due to noise, okay, also due to distortion of the channel, and therefore, basically, the AM signal is actually easily degraded in the channel as well. Then the third advantage of a FM signal is actually short. The FM signal need a shorter antenna. All right, this is due to the fact that the FM signal actually operate at very high frequency. So when the frequency is high, right, therefore the wavelength is low, right? So when you have a small wavelength, that means your antenna required is shorter. Okay, so this is in contrast with the amplitude modulation signal, where we actually use a lower carrier frequency, all right, which is in this range. Okay, you compare this and this is about what? Uh, at least 10 times less, right? So therefore, antenna has to be about 10 times longer, right? So that is the third one. And moving on to the fourth advantage, FM signal can actually transmit musical program with high degree of fidelity. All right, high degree of fidelity means the signal actually has contain more frequency components. All right. Again, this is because of its immunity to noise, the wide bandwidth, because the bandwidth is wide, therefore it can transmit more frequency components. Yeah, and also better SNR, better signal to noise ratio, with efficient use of a transmission power. All right, we have seen that in the FM signal, all the transmission power is fully utilized to transmit all the sidebands as well as the carrier component. Whereas for amplitude modulated signal, you can actually get a good quality speech out of it, but as far as music is concerned, it'll be very poor. Okay, and because one of the main reason is because of the narrow bandwidth. So when the bandwidth is narrow, that means it can only translate a limited number of frequency components. Yeah, and also because it's very susceptible to noise, noise can easily affect the quality of your music signal as well. So therefore, for AM, it's commonly used for speech communication, but not for music. And coming to the last advantage of FM over AM is that again, as I actually mentioned briefly in number 4, is that the transmission power in the FM signal is more efficiently used, right? Where more efficient in the sense that the total power is actually constant and distributed from carrier to sidebands, all right? And then of course the ratio between the proportion between the carrier component and the sideband components depend a lot on the modulation index. And for amplitude modulation techniques, we have seen that a lot of power is actually wasted in the carrier, isn't it? And this is especially true for the case of a double sideband full carrier modulation technique. Yeah, where at least 67% of the transmitted power is wasted in the carrier. Okay, so that is the 5 main advantages of FM over AM. Let's talk about the disadvantages. As far as FM is concerned, the wide bandwidth, which is the advantage, can also be a disadvantage, right? So now, if you want to transmit an FM signal, the requirement for the bandwidth is greater than AM. Yeah, and the bandwidth actually depend on your modulation index. For amplitude modulation, the bandwidth is narrower, isn't it? Because for AM, your bandwidth is just 2 FM, right? 2 times the highest frequency in the baseband signal. Whereas for FM, the bandwidth depend on your modulation index. Then for AM, bandwidth is narrower, 2 times of FM, and it does not depend on modulation index. All right. So the modulation index value will only affect the distribution of power between the carrier and the sidebands, and that's all, as far as AM is concerned. All right. But for FM, when you change the modulation index, you're actually changing the bandwidth of your FM signal as well. The second disadvantage of FM is that the circuits are actually more complex, isn't it? Because we need an integrator, we need differentiator, and then we need filter at different stage. So therefore, for FM modulation techniques, the circuits are actually more complex and therefore more expensive. But nowadays, expensive is kind of relative. So more expensive, basically, we are comparing it to AM. Because AM modulation and demodulation circuits basically require what? Multiplier, right? Adder, and also at the receiver, you need, if you use envelope detector, then you just need what? Diodes, right? What else? Capacitors and resistors, right? And filters. Filter basically is just again a series of capacitor and resistor. So therefore, for amplitude modulation techniques, the circuits used are actually much simpler and therefore cheaper. The third disadvantage of FM is that the sideband amplitude is not constant, right? The sideband amplitude is not constant and it depends actually on the modulation index. Yeah. And basically the sideband amplitude is, you can actually get it from the Bessel coefficient, the J. All right. So based on your modulation index, the J value will be different. Yeah. So therefore the sideband amplitude is not constant. Whereas for amplitude modulation, the sideband amplitude is always constant, isn't it? It's like Bm over 2, right? Yeah, so you can easily compute your sideband amplitude for AM, but not for FM. For FM, you need to actually make use of your Bessel function table if you want to find out the sideband amplitude. Okay, the fourth disadvantage of FM is that theoretically the sideband extend to infinity on either side. All right. However, as for transmission of a FM signal, we are not we are not given infinite bandwidth, right? So we actually need to limit the bandwidth of our FM signal. So to do that, we normally use filter, bandpass filter, and then this filter may introduce some distortion to our FM signal as well. So you have to be careful on your filter design. Whereas for amplitude modulation, only two sidebands are produced. All right, so this is true for double sideband suppressed carrier signal as well as double sideband full carrier signal. But if you use a single sideband or vestigial sideband techniques, then only one sideband is being produced here. Okay, so that basically end end chapter 4. Do you have any questions? If you have question, please turn on your mic and ask. No question? If no question, then I'm going to stop here and I'm going to proceed with the tutorial question discussion. Hey, very quiet. Are you all still with me?
Yes, I still continue with you.
Okay, thank you for responding. Okay, wait, my tutorial 3. Oops, I close it. Let me open back my tutorial. Okay. Okay. Which question will I discuss? Let's discuss question 8. All right, let's discuss question 8. So in question 8, in question 8, we have a FM modulator with a modulating signal MT equals to 5 sine 3000t. So again, for simplicity's sake, we just make use of a message with a single frequency. The carrier signal is 8 sine 6.5 times 10 to the power of 6t, and the modulation index is 2. Right, so for part A, you need to find the number of significant sideband frequencies and their amplitude. All right, so how to find out how many significant sidebands this FM signal has, or this the signal produced by this FM modulator has. All right, and you also need to find their amplitude. So the only way the only way that we have learned so far is to make use of the Bessel function table. All right. So now our modulation index is 2. So if you refer to your Bessel function table, all right, when the modulation index is 2, make sure you have this appendix handy during your midterm test, because you're going to need it. All right. So when your modulation index is 2, you can see that the sidebands is only up to 4. All right, it's only up to J4. So therefore, we have 4 pairs of significant sidebands. Yeah, when your modulation index is 2. All right, and then how to find the relative amplitude? To find the relative amplitude, as I mentioned in the lecture before, is to take the Bessel coefficient, the J, and multiply with the carrier amplitude. All right. So you multiply J1 with the carrier signal amplitude. So 0.58 multiplied with BC, then you get your amplitude for your first sideband. J2 stands for the Bessel coefficient for your second sideband. All right. And to find the amplitude for your second sideband, basically you take J2 multiply with BC. Yeah. And what is J0? J0 is your carrier component. All right. Bessel function for your carrier frequency. So therefore, you take J0, you multiply with BC, you get your carrier signal amplitude. Yeah. All right. So I'm going to share with you here. Yeah. So this is the for question 8. Can you see my screen now?
Yes.
Can you put full
Can
screen, please?
Huh? Say again.
Full screen.
Full screen. Okay. I think I need to enlarge it as well. All right. So again, from your equation, okay, always make use of your equation. The equation is given to you for a reason. So my message is 5 sine 3000 t. My carrier is 8 sine this 6.5 mag t. All right. So from here, I can straight away deduce that my message signal frequency, because again, this 3000 is omega, isn't it? Right. This whole thing is omega. All right. So in order to find your frequency, your message frequency in F, you have to take 3000 divided by 2 pi. All right, that will give you your baseband signal frequency or your message signal frequency of 477.5 hertz. And for the carrier signal frequency, again, this is your omega c. All right, you should be able to recognize whether this is FC or omega c, you know. So again, if you go through the questions in the tutorial, you should be able to know this. I know there are two groups that I haven't done the question 1 to here. All right. I'll do it this week. Yeah. So basically this is lecture, so I want to discuss a question that is common to all three groups. Okay, so we have, so this is omega c. All right, so omega c again, if you were to find the FC basically is omega c divided by 2 pi, right? So that will give us the FC equals to about 1.0345 megahertz. Okay, and then for modulation index equals to 2. All right, so we need to, again, from Bessel function table, which I just show you just now, is that we have our number of sideband pairs equals to 4. So n equals to 4 here. All right, therefore the amplitude, we are asked to find the amplitude of all the components, right? All the frequency components. So to find the carrier amplitude, which is V0, we take J0 multiplied with BC. All right, so J0 is 0.22, BC was 8. So that gives us the carrier component. This is FC, which gives us a carrier component of amplitude 1.76 volt. All right, and then for first sideband, all right, to find the first sideband amplitude, we call the first sideband amplitude V1. We can find it by multiply the first Bessel coefficient or J1 with VC. All right, the Bessel coefficient for first sideband, which is J1, multiply with VC. That will give you the amplitude for the first sideband signal. So this is 0.58. 0.58 is your J1. Again, VC is 8. So that will give you a first sideband amplitude of 4.6. So, all right. And this first sideband happened at FC plus minus FM. All right. So FC is this, FM is this. I remember. I don't put the numbers now because the number you can find that the number is kind of not rounded up, so it'll be very messy. So I keep it as using a symbol. All right. Then for second sideband amplitude basically is I use P2 to represent, and this is a product of J2 times PC. All right. J2 is 0.35 from Bessel function table, and then VC again is 8. So that gives us a second sideband amplitude of 2.8 volt. All right, and the second sideband actually is at FC plus minus 2 FM. All right, these two tells you that is a second sideband. Yeah, and then for third sideband amplitude, which is V3, is equals to the product of J3 and VC. All right, again, J3 from the Bessel function table is 0.13, VC is 8. That gives us a third sideband amplitude of 1.04 volt. All right, and this third sideband is at FC plus minus 3 FM. Okay, these three here represent the third sideband. Then the fourth sideband, okay, V4 again is a product of J4 DC. So J4 from your Bessel function table is 0.03, BC is 8. So that gives us a fourth sideband amplitude of 0.24 volt. All right, so this fourth sideband happened at FC plus minus 4 FM. Okay, 4 represent the fourth sideband. So part B asks you to sketch the spectrum. So now with the carrier amplitude all calculated and then the frequency of the sidebands identified here, then is the sketch is actually quite straightforward. Okay. So for carrier frequency FC, all right, the amplitude is 1.76. First sideband is at FC plus FM and FC minus FM. The amplitude is 4.64. All right. And then for the second sideband is at FC plus 2 FM and also FC minus 2 FM. The amplitude is 2.8. All right. Then the third sideband, all right, is amplitude is 1.04 and the fourth sideband is 0.24. All right. Okay, so I want to take this down first before I proceed. Or you want to take the first part here first? Mm. Okay, let me know when you're done, then I move on.
Mistake.
Hmm.
For a question like B, right, we have to draw the spectrum, right? You prefer us to write the frequency like what you wrote here is like FC plus FM, or you prefer the actual value?
Okay. Of course, you can put the actual value down will be better. Yeah, but in this case, you can see that the actual value is kind of quite a long values to write. So you can actually write this way, but you must actually state what is FC and what is FM. You also have a choice, right? Let's say you want to have good numbers or beautiful numbers to actually write here. You actually have a choice to plot your spectrum in omega. All right, you can plot your spectrum in omega. So again, if you want to plot your spectrum in omega, then you no need to convert long. So you just take 6.5 meg plus minus 3k, all right, and plus minus 6k and so on. So you can put the numbers down here. Okay. So of course, I know a lot of you will prefer to write this way: FC, FC plus FM, FC minus FM. However, in the answers, I'm going to look for these two value of FC and FM. All right. So if you want to plot this way, make sure you state what is FC, what is FM. All right. If you don't state, then you have to put the values down here. Does that answer your question?
Definitely. Thank you, Miss.
Yeah. Okay. Shall I move on?
Sure.
Okay. So next question is on find the unmodulated carrier power for the FM modulator. Assume the load resistance to be 30 ohm. Okay, this question again is very easy. So carrier power. So as far as FM is concerned, because the carrier, this is your carrier equation, right? The carrier equation is 8 sine something. So it's a sinusoidal signal. Amplitude is 8. So the carrier power is just Vc square over 2R lah, because it's sinusoidal. All right. So just Vc square over 2R. So that will be 8 square divided by 2 times 30 because your R is 30 ohm. All right. So that gives us the carrier power of 1.067 watts. All right. Carrier power is very straightforward here. D. Actually, what actually is worth more discussion is the total power of the modulated wave. All right. So how to find the total power of the modulated wave? So in this question, since we have found the amplitude for all the frequency components, that means to find the total power of the modulated wave, we just need to add up the power of all the frequency components. All right. So how to compute the power of all the frequency components? Again, it's the same, Vc square over 2 or V square over 2. All right. So I'm going to make use of, again, since we already calculated the amplitude here. All right. So I'm going to use this equation here. All right. Total power is the carrier power plus 2 times all the sum of all the sideband powers. All right, so since we have 4 sidebands, so we need to add up all the power for the 4 sidebands, then we multiply by 2. Why 1 multiply by 2? Because we have here and we have here. All right, and you can see that these two is actually this and this are actually mirror image of each other. So I just compute one side and then I multiply by 2, that will cover this side as well. All right, so that's where the 2 come from. So again, is equals to the power for each frequency component basically is the amplitude square divided by 2, right? Or 2R because R is given. So here my common factor is 2R. So I actually put it outside the bracket. And then basically it's V0 square plus 2 times V1 square plus V2 square plus V3 square plus V4 square. All right. So these are the values I actually computed here. So I can actually straight away make use of it here. All right. So that gives me all right. So that gave me 1.0686 watts. Okay. And then next part of the question asks us to comment on the power of the unmodulated carrier and the power in the modulated carrier. All right. So if you compare our answer to C and D, all right, answer to C and D, theoretically, they should be the same. All right. But here we are getting some differences in the answer. All right. So what is, again, you need to address the difference. Where are the answers different? So, so as far as value is concerned, all right, the carrier power, the modulated carrier power is actually similar to the modulated signal power. Okay, so in this case, the power or the transmission power is actually slightly higher because of the round-up error in the Bessel function coefficients. I actually talk about this also during lecture. All right. So don't be confused when this, you get values that is, why is it larger? Theoretically cannot be larger, isn't it? All right, but why is it larger now? That's because of the round-up error in our Bessel function coefficient. Yeah. So our theory is still correct. Yeah. Okay, so let's move on to the next one. Okay, if the FM signal is passed through a bandpass filter with a unity gain center at the frequency, center at the carrier frequency with a pass band of 3 kilohertz, calculate the signal power at the filter output. All right. So basically, to answer these questions, you need to know how many pairs of sideband actually pass through the filter. All right. So if you're able to find out the number of pairs of sideband that pass through the filter, then you can easily calculate the power. All right, by only consider the power of the sideband pairs that pass through the filter. So now, how to find out how many pairs of sideband actually pass through the filter? We make use of our passband here, which is 3 kilohertz. All right, and okay, this is where the value for our baseband frequency come into use. All right, so again, we're going to, you can actually find this diagrammatically from your frequency spectrum, or you can actually work it out yourself. Okay, so if you actually make use of the spectrum here, your FM is 477.5 hertz, right? 477.5 hertz. So 477.5 hertz, if I multiply by 4, all right, so the bandwidth on one side, okay, here, from here to here, if you actually find out the bandwidth, let me use a different color. All right, so from here to here, what is the bandwidth? Oops, I don't want this color. We just need to calculate one side, and then without times 2, then we get the actual bandwidth required. Okay, from here to here, if I were to take 4.77.5 times 4, I get this bandwidth actually is 1910. All right, 1910. So if I multiply by 2 here, oops, from here to here, okay, so this gives me a total bandwidth of 2 times 1910, which is 3.82 kilohertz. All right, 3.82 kilohertz. Therefore, by passing this FM signal through the bandpass filter, you actually block, okay, you actually block some of the sidebands that are further from the carrier frequency. All right. So you will definitely block this one. Will it block this one as well? Okay. So again, to know that, you take 477.5 times 3, because you want to know whether the third sideband is blocked or not. Okay. If you times 3, that means you give us from here to here, which is 1.4 something, 1.43. Okay, 1.43 kilohertz. That means the total is about 2.8, 2.9 kilohertz. All right. So that means the bandpass filter actually pass only the 3 sideband pairs. All right, it actually pass 3 sideband pairs only from here to here. Okay, this is a bandpass filter's pass band. All right, so you actually block the third one, the fourth one. Yeah, so the fourth components will not be passed through the filter. Therefore, the power of the signal that come out from the bandpass filter will only be the power that come from the carrier component as well as 3 sideband pairs. All right. So if you were to get the answer from a diagram, it will be this way. But you can also calculate the answers according to our understanding on the bandwidth there. Okay. So again, with the passband of 3 kilohertz, okay, the number of sideband pairs that pass through the filter basically is you take the passband, divide by 2 FM. All right, why 2 FM? Because the bandwidth is equal to 2n FM. All right, we want to find our n now. All right, so I just rearrange my equation now. And that will give us n equals to 3.14. Okay, so n equals to 3.14. That means only 3 pairs of sideband pass through the filter. All right, you always round down or not round up. Okay, because it never get to pass the fourth sideband. You only pass the up to the third sideband. All right, so to calculate the power of the signal that actually come out from the filter, there are 2 ways. All right, one way is again, you can add up all this power up to the third sideband. Use this equation again. All right, but omit the fourth sideband. That will give you your answer. There's another way is you make use of your power ratio. All right, making use of your power ratio is always much easier. Yeah, so here power ratio basically is the J naught square plus 2 times all the sum of all the square of the coefficients. All right, so now because you only pass 3 pairs, so we only compute out to J3. All right, do not calculate J4. Yeah. Okay, to find the power again, you just multiply with PC lah. So PC is 8 squared over 2 times 30, isn't it? So again, you put in the number for all the J's. All right, and then you get the power that come out from the filter being 1.067 watt. Okay, and let me finish off the last one before I give you time to copy. So you are asked to comment. Oh, why am I having a problem with my PDF? Okay, comment on the quality of the output signal in F. Oh, can you make a correction in your tutorial question? This should be F, yeah. F is this one here. Okay, meaning I want to know the quality of the output signal that come out from the bandpass filter. Is it good or is it not good? All right. So if it's good, then you have to say why it's good. If it's not good, then you have to say why it's not good. Okay. So in this case, we can easily say that the output signal quality is good. Okay. So how do we know it's good? Because it actually contains more than 98% of the original signal power. Okay. So again, remember this magic number 98%. Right. Whether a signal quality is good or not depend on how much of the original signal power is being transmitted. Anything more than 98%, meaning the signal quality is good. But less than this, that means the signal quality is not good. Right, so let me again start with okay. Let me know when you finish. Okay, let's take a short break here, yeah, shall we? Have you finished copying?
Yes, please.
Okay, so let's take a short break and then we shall
No, I'm not yet.
resume. You haven't?
Ah.
Oh, okay. Okay, let's take a short break and then let's resume at 12:15, yeah?
Okay.
Okay, I'm done.
Okay. Okay, welcome back. I've just launched a poll. All right, I have a question that I need some input from you. So please put in your answers. I'll give you 10 minutes. Tessa, 2 questions only. 1 question on AM, 1 question on FM. Hmm. So these 2 questions you need to complete within 1 hour. All right. So if you have done the tutorial questions, and then you actually follow my discussion during lecture as well, you should be able to complete it within 1 hour. All right. And if you haven't, if you have not been following, you know, you just say a copy result or snapshot the answers, I study later, you know, that kind of thing, then I think you will have problem finishing it in 1 hour. Okay. Last minute only you will find out, where to get this? What's the formula? You know, even though it's open book, yeah, open book, no worry. But that you may not have time to actually go and open the book, you know, and going to search from what page 1 to page 100. No way, man. So you need to maybe get all your equation ready, you know, all the formula ready, then you can straight away make use of it. Okay. So the assessment is open book. So make use of the open book lah, yeah. Don't expect yourself to search for one line of information in 100 pages of lecture notes. You definitely don't have the time for that. Okay.
Miss,
Yes.
you say the question is amplitude modulation and frequency modulation, right? So it
Yeah.
means major of them are calculation question.
Yeah, you have some theory, also you have some calculation. Majority is calculation, but you also need to have theory lah. You don't know the theory, then you won't be able to do the calculation also.
Oh, okay, understood.
And don't expect that you'll be bulat-bulat like your tutorial question. It may not, no? Okay. All right, so let me look at the answers to the polls that I asked. Okay, not too bad. 40. I have 42 replies so far. And how many of you here? 42, 54 here. So that means I have 12 more reply. Why is taking you so long to reply to a simple question like that? Unless they are not online. Log in and do something else. Am I right? Okay, so far from the poll results, Okay, it looks like majority of you find this course a bit hard at the moment. You need more practice. Yes, definitely you need more practice. Okay, where 8 vote actually say easy can follow, wow, which is good. All right, if you find it easy can follow, that means you have a chance of scoring A lah. But if you find it a bit hard, need more practice, and you actually do the practice, then I believe you can also get a B or even up to a A. All right, but if you don't bother to practice, you'll be lucky you get a C, or even pass the test. Okay, so I'm going to move on to, I'm going to keep the poll open just in case some actually join the class later. So I'm going to move on to discuss the next tutorial question, which is question 10. Okay, let me get the question out. Okay. Here to show. All right, in question 10, you're asked to design an Armstrong indirect FM modulator to generate a FM carrier with a carrier frequency of 98.1 megahertz and a frequency deviation of 75 kilohertz. All right, you have a FM generator that produce 100 kilohertz carrier frequency and the frequency deviation of 10 hertz. Right, and then the stockroom also has an oscillator with adjustable frequency in the range of 10 to 11 megahertz. You can also make use of a bandpass filter with any center frequency, and there are also plenty of frequency doublers, triplers, and also quintuplers. Okay, quintuplers means times 5. Okay, so again, for Armstrong indirect FM modulator, all right, the block diagram is pretty standard. All right, the block diagram is pretty standard, which look like this. All right, we're going to pass our baseband signal or message signal through a narrowband FM generator. All right, so this narrowband FM generator is going to generate a FM signal, a narrowband FM signal. Okay, and that will give us of a carrier frequency 100 hertz, 100 kilohertz, and frequency deviation 10 hertz. Okay, so then we pass the signal through first stage of frequency multiplication. All right, where the multiplying factor is N1 to give us the second carrier frequency, FC2, and the second stage of the frequency deviation, where I call it delta F2. All right, and then this signal is then mixed with another signal of a frequency somewhere between 10 to 11 megahertz. All right, again, the purpose of this mixing is to change the carrier frequency. All right, so what we need to change the carrier frequency, later you're going to find out that the multiplication factor required for the carrier frequency is not the same as the multiplication factor required for your frequency deviation. And therefore, you have to shift your carrier frequency accordingly. If you keep on multiplying, that means the multiplication factor for your carrier frequency and frequency deviation will be the same now. All right, in this case, if you actually do a quick calculation, you'll find out that they are not the same. All right, And then to shift the carrier frequency up or down, again, depend on your carrier this ratio, all right, between your FC5 to FC1. Then the output of a mixer, all right, will contain some components, all right, with the frequency FC3, okay, carrier frequency FC3, and then the frequency deviation delta F3, all right. You also need to know that the mixer does not change the frequency deviation. Therefore, delta F3 is actually same as delta F2, right? This signal is then passed through a bandpass filter. All right, bandpass filter is to actually select, all right, select the actual FC4 that we need. All right, and of course, the requirement for FC4 is that it must give you, all right, after multiplying with the multiplication factor of N2, it must give you your SV5 that is stated in the requirement of 98.1 megahertz. Okay, and then your delta F4. Okay, again, the bandpass filter will not change your frequency deviation. The bandpass filter will only allow the signal of a frequency FC4 to pass, or center around FC4 to pass. All right, the frequency deviation remain unchanged. So therefore, delta F4 is the same as delta F3 is the same as delta F2. All right. Okay, what is delta F2? Delta F2 basically is N1 times delta F1, right? Then this delta F4, all right, after you multiply with N2, all right, it should give you your final delta F of 75 kilohertz. All right, so you state down all these conditions in this block, then it'll be easy for you to do your calculation later on. Okay, so now let's do a quick calculation for the ratio. All right, so if you take FC5 divided by FC1, all right, 98.1 meg divided by 100K, that gives you a multiplication factor of 981. All right, that means we need to multiply the carrier frequency of the narrowband FM signal by 981 times in order to get the final carrier frequency that we want. Yeah, but what about frequency deviation? Frequency deviation, if you take the ratio of delta F5, which is the final one, over the initial one that come out from the narrowband FM generator of 10 hertz, so that will be 7,500 times. All right. So this actually is our N1 and N2. All right, N1 times N2 will give us should give us 7,500. All right. So from these two calculations, you can see that the multiplication factor required for frequency deviation is much higher than the multiplication factor required for your carrier component or carrier frequency. All right. Therefore, this mixer need to shift down the carrier frequency. All right, it need to shift down. Yeah. So let's proceed with the calculation. So FC3 because it's the output of a mixer, therefore FC3 can have any one of these four values, isn't it? FC3 can be FLO plus minus FC2 or FC2 plus minus FLO, right? And we know that we need to shift down the frequency of FC2. All right, we need to shift down. Therefore, we are going to do on the minus. All right, FC2 is supposed to be FLO minus FC2 or FC2 minus FLO. All right, that actually narrowed down our working from 4 different frequencies to 2 frequencies. All right, so let's take let's take the first one. Okay, FC4 equals to FLO minus FC2. All right, And FC2 basically is N1 FC1, isn't it? Right? We multiply FC1 by N1, we get FC2. Right? So substitute FC2 as N1 FC1. All right. Then what about FC5 then? All right. Okay. So you may ask, no. Here I say FC3, but why here I put FC4? FC4 again is either one of these four frequencies, isn't it? Because we actually pass the result of the mixer into a bandpass filter. We just want to select one frequency. So FC4 can be any one of these four frequencies. All right. So here I'm going to take minus, okay, because as I mentioned before, because the ratio, the multiplication factor required for the carrier frequency is lower than the multiplication factor required for the frequency deviation. Therefore, I use minus. I start with a minus. Yeah. So FC4, I choose it FC4 to be FLO minus FC2. All right. Then how do I relate FC5 to FC4? Okay, FC5 basically is N2 times FC4. All right, from this diagram here. So I know FC5, I know FC1, I know N1, N2. So therefore, I substitute FC4 into this equation. So FC4 is FLO minus FC2, right? Which is N1 FC1. So FLO minus N1 FC1. All right. So again, I multiply out and then I collect the terms because I want to find N2 first. All right. I know N1, N2, I know FC5, I know FC1, FLO, I know the range, right? So I can find my N2 range from this equation. All right. So to find N2 range from equation, then you need to substitute the value of FC5. All right. Substitute the value of FC5 in, which is 98.1. N1, N2, or N2, N1 is 7,500. FC1 is 100K. FLO is somewhere between 10 meg and 11 meg. All right. So if you press on your calculator, all right, when your FLO is 10 meg, you get FC N2 value of 84.81. All right. And when it's 11 meg, then you get N2 of 77.1. Then that means your N2 can be any number between 84.8 to 77.1. Okay. Remember, we can use doublers, triplers, the frequency doublers, frequency triplers, and frequency quintuplers, meaning we can times 2, times 3, and times 5, right? So maybe a good value within this range is 80. All right, 80 is equal to 40 times 2. So if you break that down, that will be 5 times 8 times 2. And break down further, that is 5 times 16, or 2 to the power of 4. So I need four frequency doublers with 1 frequency quintuplers, right? If I choose my N2 to be 80, that means my N1 has to be 7,500 divided by 80, right? Because N1, N2 equals to 7,500, isn't it? So therefore, your N1 will be 93.75. All right. How to get 93.75 from times 2, times 8, and times 3? No way, isn't it? There is no such multiplier here. Okay. So that means this frequency expression for C4, for FC4 is not suitable. All right, it's not suitable. Then we're going to try another one. Okay. All right, we're going to try another one where FC4 is FC2 minus FLO instead. All right. So now again, we substitute into the equation for FC5 and then we rearrange. All right, rearrange. Then you get your N2 is N2 N1 FC1 minus FC5 divided by FLO. All right. and then substitute that into your equation. All right. Then you get N2 can be any value between 65.19 to 59.26. All right. So if I choose N2 being 60, again, 60 is a product of 5 times 12. 5 times 12, you break down further, is 5 times 3 times 2 times 2. All right, that means I use one frequency quintuplets followed by one triplets and two frequency doublets. All right, that will give me a multiplication factor of 60. All right, from N2 being 60, N1 will be 125. All right, 125, I can easily realize with 3 frequency quintuplets. All right, because 5 times 5 times 5 will give me 125. Okay, so now I have got the value for N1 and N2. The next one is I'm going to find the value for my FLO. All right, so to find the value for FLO, just rearrange your equation here. Bring your N2 down, bring your FLO up, and then you will substitute the numbers in. Then you get your FLO will be 10.865 megahertz. All right, so this is within the 10 to 11 megahertz. So we can easily tune our local oscillator frequency to 10.865 megahertz. Okay, and then the last thing you need to find is the bandpass filter. What kind of bandpass filter do we need? All right, so the function of the bandpass filter basically is to allow the FC4 to pass through, right? Yeah, the FC4 to pass through. So FC4, what is FC4 then? So FC4, again, we actually use the FC4 equation being FC2 minus FLO here, all right, to get our N1, N2. So we substitute the value in. So FC2 is N1 FC1 minus FLO, right? So this is minus FLO here. So again, put in the number for your N1 FC1 minus FLO. Then that gives us our FC4 of 1.635 megahertz. Okay. Again, you might want to double check your FC4 answer by putting it into the equation for FC5. All right, and that should give you the same answer, 98.1, right? Our FC5 need to be 98.1, so we're okay, we're correct. So this FC4 basically will tell you the center frequency of your bandpass filter. All right, what about the pass band of your bandpass filter? The pass band of your bandpass filter, okay, this is the center frequency. All right, then the pass band of a bandpass filter comes from your delta F4. All right, the frequency deviation. So delta F4 basically is same as delta F3, same as delta F2, isn't it? Because the bandpass filter is not supposed to change your frequency deviation, not supposed to, then the mixer also is not supposed to change your frequency deviation. So that leaves us the delta F4 being same as N1 delta F1. All right, so N1 delta F1 will be 1250 hertz. All right, 1250 hertz. So basically, when you have a bandpass filter, all right, you use a bandpass filter. This is your center frequency. Okay, this is your center frequency, which is FC4. And pass band is this one. This is your delta F4. All right, delta F4 is 1250 hertz. So that means your pass band will be 2 times of delta F4. All right, your pass band need to be 2 times of delta F4. So which is 2500 hertz. All right, so your pass band need to be 2500 hertz. Then the center frequency for the bandpass filter need to be 1.635 megahertz. Right. So the design of FM indirect FM modulator basically require you to find the value of N1, N2, the FLO, as well as the bandpass filter. So we have done that in this exercise. Okay, so Any questions? If not, then let me adjust the page a bit for you to. Maybe here first. I have question. Wait, you have question, then you better ask me. You the mic is easier. Lost. Where were you lost? You stop me when you are lost. Actually, I talked about this during lecture already. It's just repeating the same thing in the tutorial questions. All right, where were you lost? Okay, let's get the answer down part by part, and then you tell me where you're lost. All right. So let's start with part 1. You want to take this down first? Let me know when you're done, then I scroll down. Yeah.
Miss, this part done.
Okay.
Miss done.
Okay.
Miss done.
Okay.
Done, Miss.
Okay. So let's end the design by actually putting in the final design values. Okay. So we have our message going into a narrowband FM signal generator. That gives us our FC1 equals to 100 kilohertz. Our delta F1 is 10 hertz. All right. Then it go into a frequency multiplier with the N1 is 125, right? Yeah. And then followed by a mixer. All right, where the FLO for the mixer is what is it? 10.865 megahertz. Okay. Then it goes through a band pass filter. Band pass filter where the center frequency is 1.635 meg, and then the pass band is 2.5 kilohertz, right? Then followed by another frequency multiplier. N2 is what, 60, right? Yeah, 60. Okay, and that will give us the final FC5 of 98.1 megahertz and our delta F5 of 75 kilohertz. Okay, so this is how your design look like. Okay, so your band pass filter, sometimes you say is the pass band equals to 2.5 kilohertz. Sometimes you say the bandwidth is equals to 2.5 kilohertz. All right, so they are the same one. Okay, so yeah, just now someone say he's lost. So where were you lost? You want me to go back and explain from there? Or you might want to go through this thing again at your time, at your pace, and then if you still find it hard to understand, then you can always ask me again in the next session. Okay, let me see. Uh, understood. Oh, understood already. Oh, okay. Okay, so yeah, anything you want to say? Let me check your poll answer again. Have I got everybody to answer? Okay, looks like, yeah. Okay, answer is good. But I think I haven't got everybody to answer. So that means some people are not answering. Why? Oh, okay. If you actually attend the class using handphone, then you won't be able to answer the poll, right? That's the way I understand it. Okay. So if no questions, then we should end the class here. Yeah. Then I'll meet you again during your tutorial session and also the lecture on Wednesday. Okay. All right. Bye bye then.
Thank you, Miss.
Thank you.
Thank you, Miss. Bye bye.
Yeah. Bye.
Thank you, Miss.
Thank you.